James is the Application Technology Manager within the Metal Systems Group of BASF 3D Printing Solutions, forward AM. His current focus is development and optimization of metal filaments, additive manufacturing materials, and systems. As an advanced application engineer, he focuses on additive and subtractive manufacturing system, including direct energy deposition, 3 and 5-axis CNC machines, and rotary ultrasonic machining. That was in the past, actually. While earning his master's in mechanical engineering from University of California, Davis. Go Aggies. Aggies, yeah. I'm an alumni myself. His research focused on the parametric optimization of rotary ultrasonic machining for the production of Zerodur glass, ceramic, optical, and structural components. I want to just touch on the personal side. I remember the days that I, was seeing James at the Boehner Hall of Mechanical Engineering Department of our school, and I always looked up to him. He was an advanced level student in graduate school, and he always, was pushing the boundaries. This is quite exciting to have him. James, big thanks to you for giving us your time. And without further ado, I would like to pass it to you. I know everyone is excited to hear from you. Please take it from here.
All right. First off, thank you. Second off, logistics. Everyone can see the screen. Okay, we're sharing everything live. Okay, good. So, yeah. Again, thank you for the introduction. Welcome to Heidelberg, Germany. It's about 6 p.m. here. My name is James Pitts. Again, application engineer. No, I'm the manager now. I'm application manager for metal 3D systems. It's a fused filament process. Those who have a 3D printer at home or at work, you're gonna know what this is. So without further ado, let's go and get started. Generally, I like to go really fast, but start very early, start at the beginning. I don't know if we want to interrupt for questions or if we want to gather them. That's up to you, Farhad. Depends on what's in the chat. We can go from there. But in general, I'm going to talk about kind of what we're doing, what the process is. This is, it's a fused filament. So, let's just watch it print, So 3D printing, desktop 3D printers. Many of you, like I said, probably have one either at work or at home. I got 3 at home myself. I can use this material at home. You have a spool of filament that takes basically a plotter and a glue gun and combines them to make material. And you can see here, this is our material, Ultrafuse 316L. So let's first kind of talk about what it is. As mechanical engineers, I'm sure we're kind of familiar with 316L. It's very popular in many applications, food, chemical, high corrosion. So this one's definitely more of a corrosion environment for this. And what you're seeing here, those parts are printed from a 3D printer at home. Now, Ultimaker or more prosumer, but our goal is to make this product work on everything from the homemade machines at home through prosumer into professional machines. So our guiding principle is that it should be, I can do it at home on my Prusa Mini. Done. We also introduced recently 17.4. It's a precipitation hardened stainless steel. If you're looking for a little bit more hardness, toughness, and you want to employ some H900 like heat treatments and things like that, that's now in the books. And these two materials are very, very, very frequent in many applications. And I'm going to talk a little about metal injection molding later on to kind of bring up the introduction, but as I said, we over the potential applications. I like to say the sexy part is it's metal. The boring part is it's just steel. Mill it, grind it, weld it, make stuff out of it. And kind of an example is this valve block that we made. I can, on the camera, I can show you. It's about that big, right? So coming from a 3-axis, 5-axis standpoint, this is a difficult part to produce, right? Multiple setups, thin walls, all kinds of features like that. I made this on a $400 Mini. I'm not saying that Prusa is the best printer. It's the best one I own, but I could not make that part without a ridiculous amount of material and warm up and knowledge and experience. And I certainly couldn't make it for $25. Right. So this kind of has a key indicator of what this technology can do. We're you know, I don't like to use the word disruptive. It's a sleazy business word, but this is disruptive. I got a master's in mechanical engineering, focus on CNC machining, and I can't do this with a $5 million laboratory in 2 hours, right? So first, let's talk a little bit more about material properties. After all, we are MEs, right? So there's a smattering of the critical material properties of each of these two materials in their centered state. As you can see, they're going to be a little bit lower than wrought material. But that being said, of course, I always get that question, oh, but it has layers, isn't it weaker in that layer direction? And I always remind people that I never see carbon fiber in compression, right? We are engineers. We take natural laws and processes and try to make efficient, responsible things by understanding what those laws and principles are. In this technology, there is that layer effect. Real quick, I'll get through how does this stuff work, because this is stuff you can buy. This is stuff I bought. We have two ways. Do it yourself. You go to a distributor for American market. That's going to be Matter Hackers. You go on Matter Hackers website. You buy the spool. You get it. You print it. It comes with these coupons. Those coupons go to the debinding and sintering ovens, which we're going to talk about shortly. And you get parts that come back in around 2 weeks. Other people, they don't want to print. They don't have a printer. They're not into it. Well, we also have a platform called Sculpteo that we acquired. You download your part. It gives you a thing, tells you how much. It's back in 2 weeks. So I like to think of that as when people are like, I don't know if I want to do it. But I said, try it before you buy it. Get a part in your hand. See what it looks like. You know, we can go from there. All right. So now we're starting to talk about like the actual, what differentiates this thing. It's an FFF filament. It's I might call FDM if Stratasys patent situation been, but in general, this is you close your eyes and you think of a 3D printer on your desktop. That's what this is. The only difference here for us is that we have a highly filled, and there's a spool right there. It's under my desk. It's just a regular filament. It's just a metal powder, not as fine as, say, powder bed, and therefore we have less problems with health risks. That finely packed powder into a polymer binder. We use that binder to get the metal into the right shape. We then use debinding, which just removes that binder, leaving with kind of like a porous sponge of metal. And then we sinter it like we would any other press and sinter or MEM product. We would just make a full metal product after that. So to talk about our stuff, we have to kind of talk about metal injection molding. Even as a manufacturing nerd myself, I wasn't really familiar with this until I joined the BASF group. Metal injection molding is much like, almost exactly like plastic injection molding. You have a mold, you have a molding machine, you have feedstock, you press it into the mold, and what do you get? You get high complexity parts that are a certain size, usually about 100 grams or so, quarter pound. High complexity, all kinds of features, high quantities. If you look down at that Apple lightning connector, you may or may not see, you know, that kind of features, that kind of part. So high quantities, high strength, and large. We've been doing this for 30 years. So my material is the grandson of the metal injection material. We're converting it from those who have an injection shop that have all these equipment to the kid on the street, the university student, or the R&D person looking to make rapid prototypes easily. So this here, you're seeing here, this is the metal injection molding path where we go from a feedstock, we inject it, it's green part, debinding, brown parts, sintered metal. And these names are coming from the ceramics, like green ceramics. You might have heard that before as an unfired ceramic. So what do? We provide this entry loop. It's the same fundamental product chemically. We can take advantage, you can take advantage of economies of scale already set up for metal injection molding by putting it in an existing batch. Maybe there's an automotive run that's doing 1 million parts. We can literally run within the uncertainty of their batch sizes. We can provide that disrupt, and I like to think of we're a disruptor and a force multiplier. You can print something, have a product, version 1, knowing that you can go and get it injected, knowing you can get it cast or machined for version 2. And people say, well, I don't know if I can do that. And I remind them, for those of us that remember the iPhone 1, it had no app store. Would any one of you buy an iPhone without an app store right now? Of course you wouldn't, but it proved the market was there. And then you could move forward and you could advance the technology. And I've seen our technology do that with multiple runs of product. Again, you print it, you debind it, and you sinter it. So we're done printing. We've printed our part. It looks good. Well, we have that metal powder combined with the binders. And those binders, the main binder is polyacetal or POM. There's some secondary backbone binders that we're going to talk about during the sintering process. But what sets this technology apart from your traditional printing filaments you have is this debinding and sintering. So we use nitric acid. In German, it's Torpedosäule. I can never say it right. We use nitric acid. That nitric acid wants to work on the POM. It wants to degrade. It wants to catalyze and do that. But the takeaway from this is this takes hours, not days. It's a gaseous product. You're not soaking it in water. You don't have barrels of stuff and chemicals sitting around your shop. This is done at an industrial site. Those questions you're having in your brain, you're thinking, can I do this in my oven? No, no. This is nitric acid inside of an oven. Now, as a mechanical engineer, I promise this to be the only chemistry slide in my presentation. But as you can see here, the POM binder that we have here, it decays into formaldehyde in nitric acid. Now, this is happening below the printing temperature because we want to maintain the shape of the part. We don't want it to sag and break and things like that. But this formaldehyde is then vented off and combusted. This is done at our facilities. It is a safe process because we're doing it at large scale. You're thinking, we talk about literally, I like to say MEM is nuclear. We talk in megatons sometimes, right? This is done at an industrial process, and it's done much, much faster than other solvent properties, other methods. Okay, you made your part. You got to go in the oven. What's the oven look like? It looks about like this. This is the oven, and you can see, I don't know if you can see, I'll bring on my fancy laser pointer. This little benchy boat, standard 3D printing fair. Well, there he is. So that'll kind of give you some scale, right? I put my parts in there. We put the parts on these ceramic plates. We put those on the plates because if you put it in a sintering furnace, you will weld. And that's a method we've used before to make assemblies of parts, is welding it. It's on that ceramic, so that way it doesn't weld to the oven. So now you've debound it. We introduced nitric acid into the atmosphere of the oven. We've safely contained it, burnt it off, and now you're left with a brown part. Brown part is, I like to think of like a sandcastle. The best analogy I can have in my brain is like a sandcastle. You have a powder granulate, you have a binder holding it together. In the sandcastle, of course, that's water. In this case, we're gonna have secondary binders. And like a sandcastle, if you have too much, it's a problem. If you have none, then you have a thing of powder. So it's important to get that sintering. Now, Wikipedia once told me that sintering is the process of compacting and forming solid masses by heat, pressure, and without melting. Again, we're doing this, we don't want to have a puddle of metal. We want to combine and build conglomerate grains out of those individual powders. And during this time, that combination process, you get a small size. The empty space comes back together. Now, these two processes I'm going to show you are happening on the same time scale. The one on the left is just temperature over time. The one on the right is the size change, the shrinkage, basically. And you can see at these points, just like any other material, as it gets hotter, we start to get bigger, right? Once you start getting up around this 1200 degrees mark, then you start fusing. And that's when you see that grain growth, that creation of dense structure down through the process. So all this is saying is that it gets hotter until those want to fuse, they want to neck, they want to reduce their surface energy and become one big part, producing a full metal part. Now, this little gray box I put here, I affectionately call this the Valley of Death. The Valley of Death. Why is it a Valley of Death, James? Well, because that sandcastle isn't become glass yet. So if we get all the water out of it too quick, it's just going to be a pile, right? So a lot of these design guides, and I'm going to give you the introduction through here for design guides. The motivation for most of this work I do and my research I do is to minimize this Valley of Death, right? Every process is designed to have certain needs, and every part has certain needs, right? And we're going to get there. The good news is a lot of it's basic engineering. Real quick, kind of what's an oven? How big does it look like? Well, a standard human being can stand at that. The one on the left is for sintering. The one on the right is for debinding. Now, our provider, so you bought your material, I buy my material, I get done, I ship it. It goes to, if you're in the United States, it goes to, not Detroit, it goes to New Jersey. Beautiful, beautiful New Jersey. If you're in Europe like me, it goes to the beautiful Black Forest. Both of those are ran by a company called Elnick Systems. They make these ovens. We chose them as a provider because they make them. They're not just people running it. They actually build custom designed ovens for the MIM industry, and we know that we're going to have the best service with them. So where does it go? How big is the oven? Okay. And design guide. This can go really, really deep. So my cheesy sales shtick is a great part start with great design. You've had those classes. You know to put a fillet on something. You know why. Every single process has its own special needs for design. Many of you in various I mean, I used to work for DMG Mori in Chicago and California, and you get a part and you look at it and say, oh, can we make this? And it's like, well, no, this is a difficult part to machine with a CNC, right? How am I going to get inside there? How am I going to do these things, right? Or I can print it on my printer, right? It has to meet these design criteria to improve. Now, these are made as recommendations, not limitations. Some of my parts I'm going to show you what the rule of thumb is, and then I'm going to show you why it's there. I've literally written these rule books by failing and writing it down and showing. It's a limitation, not a thing. Printing is the easy part. I'll show you parts you can print, no problem. It's the debinding and sintering that's that petrol. Remember that Valley of Death that we're going to fear and respect. And this is a living document. I've been at this for 4.5 years now, and the things we're making, like my little gear I'm sitting here fiddling around with, right? We couldn't make this when I got here. So movable, functional, multi-element parts. This is a living document. And I challenge my customers, my friends, my users, show me your part. Let's highlight it. Let's talk about it. How'd you do it? You gotta tell me how you did it though. Okay, shrinkage. One of the biggest ones, the big differences too here is that during that sintering process, when that part shrinks, right? Therefore, you have to scale it up. You have to scale it up to prepare it to hit back down to that spot. So these shrinkage factors are our standard shrinkage. Sometimes they're going to, there's some geometrical effects we can talk about, but in general, these are my starting positions. I'm an X and Y. They shrink at about 16, 17%. right? Z has the gravity assisting it shrinking and falling down. So it shrinks a little bit more. You imagine X and Y, as it's sitting on that plate, it has friction holding it back. Z pushes it down, and that's why you have anisotropic shrinkage, right? So you might hear when people talk about, oh, it shrinks between 17 and 20%. No, it does not. X and Y is around 17%, and Z is around 20, right? And on the picture on the right, you can see these are scanned with our GOM scanner. The left is the centered, and the green is the final part. Not the most beautiful part. It was a research part looking at surface quality and parametric optimization. So, okay, so I've got my part. I print my little chess piece. I like chess, so you see a lot of chess pieces. Then it comes in, because one of those obvious questions is going to be like, oh, how accurate it is. And I'm going to show you it does depend. This chess piece, I don't think I have a giant one. I have a bunch of them. There's one I painted, that kind of thing. He's not 100% full. He's hollow. That's one thing I didn't touch on. It's one of our unique properties is you can make fully hollow parts if need be. You can make parts. We've made parts that float. I don't think I have it. It's somewhere else. But you can literally make parts that are hollow in the inside that could not be made by traditional methods that I'm aware of. Unless you're doing multiple assemblies and things like that. So I take my part, I measure my green part, it comes back, I measure my metal part, and then down here, we have our actual corrected size values. So remember I said it was 1.2 in XY and 1.26, just bring it here, 1.2 and 1.26. Well, for this specific geometry, it shrank a little bit less than it wanted to be in the X and Y and a little bit less in the Z, and you can correct that. Now, you might be saying, yeah, but then I have to wait all the time to do the next one. Well, with a small part, print 4 or 5 of them at slightly different scales, and then you have it on the right side. Now, coming from CNC, the first part's never right. You'll break a tool on every first part. Injecting, same thing, right? Casting, yeah, hard, right? So it's these design guides, right? So take the advantage of additive manufacturing. I tell students, my interns, is, hey, print 5 of them and see which one works. Just do it. Just make it. See what happens. But in general, it's reliable inside of its part. So the part-to-part differences are minimal compared to that first shot. One of those questions you're going to ask me is, how big can it be? Right now, 100 millimeters cube. Why do we do that? The simplest answer is that those ceramic plates that we showed you, those are about 100, right? If it goes any bigger, it's got to sit on a different plate. We can order special plates, but all of that becomes a custom solution that'll take longer and cost a little bit more. If you want to use the ready-to-go process, keep it inside of 100, right? Small is the new big. And for a new user, which these guides are, this material is really oriented toward a brand new user, sweet spot is about 60. Stay small. And like I say, thin pancakes, not pillars, right? Think of masonry. I don't know, I'm a history buff. I moved to Germany. I can look at castles, you know. Think about how they're designed. This is a material that is good in compression when it's in that sandcastle state. Look at the crenellations on castles. Look how it's set up. Think compression, right? Flat. The real sweet spot is that 30, that's smaller. So about 2 inch by 1 inch tall is about right. Now, I told you I'm going to show you the rule, and I'm going to show you what happens when I break the rules. This part on the right here, this big king, I mean, here's the big queen, hollow in the inside. Actually, I know where one is. We had to literally take parts out of the oven to get this thing in the oven. Very custom job. You can see, here's my buddy right here. Now, we took a wire EDM and we cut it so I can show the inside, right? I made this to mess with my friends in CNC because I can take it to them and be like, hey, can you make this? And they're like, come on, James. That's like the simplest turning, you know, rookie mistake kind of thing. And I said, yeah, but it's hollow on the inside. And they're like, well, you could do 2 parts. You know, it's all about the fun. You know how it is. You're talking to people that are into things. You kind of give them a challenge part, right? What we did on the side here is, imagine this shrank 20% down. So it was about 220 millimeters tall. Then as it came down, we had problems, right? First, one shot, one kill, no. We created some modern art. That's what I call that. That's modern art. But like a good engineer, like a good scientist, what do? We identify where the problem is, right? Those layers are letting go. We identify just where we need to do it. We print just the section we need to know, and then we go for it, right? So why am I telling you this? I'm telling you this because you can make big parts. I'll show you big parts. It'll be challenging. If you're new, start small. Start small. Start with the little thing on the Prusa. There's Buddy the dog, right? Polished up. Now, CNCing this thing, that's an expensive part. Just the license of NX Cam or Esprit is going to cost me $50,000, and getting a person that knows how to run the thing, probably even more. Okay, so how big is it? We got that. Now we're talking about more like height to width ratios. Again, speaking about that stability, making sure that it's stable. I want to have a good base on it, but about 3:1 is in general pretty good, right? Now, the parts on the right, these were designed for calibration of some prediction software. They're printed laying down, and then we stand them up, right? And if you can see, there's 3 of them here. So you can see it's varying a little bit, right? So that's our viscosity tower, right? We call it viscosity because I wanted to measure what kind of systems. This was centered too high, right? That metal was getting closer and closer. So we're saying it's not liquid, but it is at 1200. Well, no, it's at 1380 Celsius at max. So we need to design around that stuff, right? Now, the question in your brain should be, why didn't you just lay it down and center it? And I'd say, good job. That's how we should do it. We're using this as an example to show why. What happens when I break that rule? Then parts come out bad. If we extrapolate this or convert it to a 2D example now, it's the wall can be a little bit taller if it's a little bit supported on kind of 2 points. And you can see on the right, I had my intern print me out this part. These are the height to width ratios, and no problem. It's hard to see here, but this one's leaning back by about 15 degrees, but dead for any purpose. Now, the good news is all that time we spent and spend learning engineering still matter. You should still have a fillet. You can see this right edge on this right one. It ripped apart. It's trying to glue that next layer on a very short surface. This is another example of a design guide. Have a fillet, have a chamfer. This is regular engineering. The rules still apply here, right? These basic principles still exist. Sintering won't fix it. It's the topic of this slide. A lot of people will say, oh, well, you know, my part, I know Farad has some of this material, so I'm gonna get these. He's gonna have beautiful parts. I'm gonna help him, he's got this, no problem. But sometimes there'll be a part and you'll look at like on the right, and he's like, I can see gaps, I can see it's not full all the way, and that's gonna have a problem because they say, oh, well, sintering combines the metal. And I'm gonna tell them, yeah, but those individual metal grains need to, the average distance which will connect is about the nominal diameter of a particle. So once you don't get density in your green part, those literally can't see each other and connect. The cheesy analogy I like to say, it's like you're trying to talk to somebody at a bar. You got to go over and be close to them to see if you can make a connection, right? Same way if they're far apart. Now, if we see these splits in the geometry right here, it's going to lead to situations where delamination and things like that. Again, thinking of the density tower, thinking about the other ones, these rules stack onto each other. Supports. FDM needs supports. They're not printing. If you need it for printing, you need it for debinding and sintering. Think about how to minimize supports. This part here on the right, it was designed in collaboration with John Deere, and it's a robot gripper imagine a multiple of those coming together. There was a bunch of different design criteria we needed to realize. Round shape to prevent cutting, people minimize weight. I got one back here. This is my wall of shame back here. I don't know if you can see it. Here's an example where we made it completely honeycomb. This is a half version. You can see we were able to reduce about 40% of the mass to this thing. So imagine when that robot's swinging around, now you don't need big motors as much, you have more control, you have more accuracy. But what does it do? This was designed, or this is about version 3 design. We ended up not needing those supports there. But you can see that they're kind of bowing out a little bit. Again, we have that viscosity thing. So in the end, what did we do? We iterated a little bit and we basically printed up taller than it should be and then let it fall down to where it was. It's kind of like when Grandpa taught me how to use a shotgun. He said, all right, Jim, shoot for where the bird will be when the bullet gets to it and not where it is now, right? And we have simulations that we can help with this. We can just test it. At the same time, I tell some of my clients and some of my colleagues, just print it, try it. Be it quick and dirty. You're not tying up the fabrication facility. You're not getting all these approvals. It might cost $100. Just do it. Try it. All right. See if it works. And if it works, we can go from there. My friend Buddy. My poor buddy. Now, this is an example of something that's printable, something that's free, available, something you've seen that works. You've seen the 100 one. You've seen them polished. The one on the left has only 30% infill. So this is me kind of, what if I didn't know about this stuff? What if I just thought it was ABS plastic and went print? Well, it looks good. Part looks good, no problem. And I know, hey, this is gonna be a problem. So I print one at 70 to see if I can make it work. Indistinguishable. Now, one is half the weight of the other one, but they look exactly the same. The problem is we're in that limit. 30%, Buddy's dead, he's modern art. 70%, he's got that little crack. Like he survived, but he's marginal. You can see how his head's slumping down. It's cracking like that. And that's an example where supports are going to be required, even though they aren't required in printing. Now, it's a not very closely kept secret. We are developing a ceramic material. We showed it before. Also a fan of art, so like that's the Venus de Milo. It's in ceramic, and you can imagine that support material. So that's things coming up. But what's the point of this slide? The slide says supports are not just for printing. Okay, other good news too is that you can still kind of get your hands dirty. You can still use the existing tools. When I worked at Machine Builder, there was more than one type of CNC machine, right? But the more tools you have on your toolbox, the more jobs you can do. So maybe you want to just be ridiculously dense. You want it to be just ugly dense, so it's stronger, so it shrinks less. Well, come in, sandblast it, mill it, drill it, paint it, right? What I'm saying here, again, the sexy thing is that it's stainless steel. The boring thing is it's just stainless steel, even when it's done. Weld it, grind it, sandblast it, polish it. I don't know, make stuff out of it. But you can still have that creative inspiration. You can still do things. You can realize these things that would not be possible in my previous technologies and positions. You start out with a block of metal, and you better have a CNC machine. You better have an angle grinder. And in this is a regular cheap vise that we printed. Since we have the model, we use TPU. For those not familiar, it's kind of rubbery, stretchable material. And we've just made jaw chucks. All right, I have guys at DMG Mori that would sit there and all day cutting jaw chucks just so they could pick up one part. We printed it. We were done in 2 hours. We threw it in there, we cut it. It's good to go. So this is really approachable for me because I know what it's like to have the high end. You want to spend as many millions as you want. You kind of miss the fact that you can kind of just get your hands and do something. If you don't like the part, if it's ugly, just kind of sand it a little bit. you can correct these things, you can fix these things a little bit. Of course, PPE, but everyone's got extra PPE now for some reason that I don't want to talk about. All right, this is really quick, I know that. So this design guide, this information, shrinkage examples, things like that, this is in the design guide. For those that missed doing algebra, I have a little example there. Reference value, take a look if you want to, learn some more stuff, figure out how to do it. QR code. If you are super excited about listening to me with my shiny fat head talking, there are probably another 2 hours of videos on YouTube that covers this material. So just kind of refresh and get a better understanding of these things. And I think as far as the prepared slides, that is it. Questions, comments, concerns?
James, wow. What a presentation. Thank you so much. This was
No
by
problem.
far one of the most exciting presentations, given that I'm heavy additive manufacturing fan as well. Thank you so much. I know there's a lot of lots of questions that people are thinking about. I wanted to show off my parts as well, our company logo with the material, and SME, for chapter 29. I made a keychain, but I haven't sintered yet, so I'm pretty sure
we'll get you there.
I'm gonna get there. So it's very exciting. I'm gonna the couple of questions came in, and I think we can open up the floor, and people, if they would like to unmute themselves. I'm going to go through the list, and then hopefully, other folks who have questions, they can jump in. So first question, are the slides possibly available as well? Can we have the slides, or is that?
We just recorded them.
Yeah, we recorded them. So
so in that way, generally, I don't like to give out all of it. I'd go ahead and share my contact information. I'd like to talk individually, kind of thing, taken out of context sometimes, because I am showing like failure a lot in there. I'd prefer to have a one-on-one and explain the thing. So
absolutely, no problem. And everyone, we have a recording, and we'll make it available in SME virtual network. So hopefully we can send you the address afterwards. Maybe James, if you can touch base, what kind of desktop printers are capable of printing with material?
Yeah, no problem. We do a heavy business with Ultimaker. They're very, very popular. Ultimaker, BCN, Race 3D, Prusa, Zerodur. If it has a 1.75 or 285 millimeter, you can print it. Basically, if I was going to somebody and talking like, what do I need? Imagine a printer that you can print with ABS, because there is going to be a little bit of warpage. It warps less than ABS, but in general, you want to get a enclosed chamber. Now, let's be honest, I went on Amazon and I bought a server cabinet for $90, and I put a printer inside of it and I closed it. Voila. Or you could spend $5,000 on a thing. So we've had everything from a $100,000 custom design machine down to interns making one from scratch. So we wanted to work on everything. We wanted to, someone said in the comments, we wanted to democratize AM, and I don't use that lightly.
Yeah, awesome. Yeah, that was actually mentioned by Jacob as well. And this is absolutely a great example of democratization. We can discuss that. I have questions on that myself, but I'm going to go through the questions that folks submitted. Safety wise, James, can you touch base if, I personally haven't seen or haven't felt like an odor coming out, like you print ABS, you print other type of, composites or whatnot. So please touch base on that. That would be great.
Yeah, no, it's a great question. Like any other 3D printed material, I would caution you about open printing, definitely ventilate. Again, I have a little computer fan that I blow it out the window. Now, ABS, you're going to smell. ABS gives me headaches, so I vent that off. For us, if we go too high, if you're outside of our printing conditions, you can start outgassing a little bit of hydrogen sulfide, which you're going to smell, you're going to start getting headaches, and you need to stop that. So stay below 250 and close it, which is good for printing anyways, and then away you go.
Awesome, thank you. Yes, and you covered about the supports and you covered about the shrinkage. So are there any other questions, folks? If anyone wants to jump in, if not, I'll ask my question. So we have I think a question about, they're coming in. 1 second, James, I'm trying to.
Yeah, no problem, no problem.
Yeah, thanks.
I saw a question about a honeycomb, and
yeah,
honeycomb is so last year's 3D
oh yeah, you
printing.
saw the question. Okay, yep.
So I don't know if you can still see my camera. Yeah, I mean, that you can see the light through it. That's going to be a honeycomb through there. So again, imagine the weight savings you're realizing from reducing that much mass. Now gyroid is sexy though, like completely hollow. And now it sounds cheesy. I had a father and a grandfather who were salesmen. So they said, go be an engineer. Right? What I like to tell people is that I don't know what the outside of your part might look like, but I can show you what the inside can look like. You want to save some gas in that car, you want to be lighter, faster, whatever, we can use regular traditional FFF methods to get you there.
Awesome. That was what an example was that. You know, that was
I've done this
sweet.
before.
Yeah. that was a very nice piece.
I literally do this for fun. Yeah.
Question came in, a very interesting one. Have you had experience of nozzles clogging or anything happening with the printer?
Nozzles, honestly, I have more problems with PET and PLA clogging than I have with this stuff. In general, hardened nozzle, that is a good question. I've used you can use a brass nozzle. It's got great thermal conductivity and works good. You'll start to get nose wear because it is kind of abrasive. You'll start wearing down the nose. And if you keep the first layer right, then you're okay. Some people want to go buy a ruby. Some people want to go get a hardened steel nozzle, which you can do, go for it. Basically, I buy a printer, I run that brass nozzle until it doesn't work anymore, I throw it out, and then I go get a stainless steel nozzle. And the guidelines, we'd like to say a new nozzle every 3 kilograms.
Sweet, perfect. There's one chemical debinding method. What about metal printing? Great question, thank you. Yes, metal printing.
Excellent question. Printing, no problem, right? The printing, no problem. If it sticks to palm, it sticks to palm. We can do that. And like I said, the grandfather of this is that metal injection molding. So there's 8620, 174, like it's wide. Sintering is where the multi-problem. You need to find two materials that want to have the same sintering conditions. Like a lot of time with 316, we're trying to make sure that we're not, or like with carbon content, we have to keep our carbon content below 0.04%. If you have something that's more carbon rich, you're not going to have 316 anymore, you're going to have metal, and that just depends on your thing. So find me two materials that I can sinter together well, and let's do some testing.
Awesome. Yeah, that was a great question. I'm going to read another question that came in. I hopefully have some time for my question. What was the biggest size of the mission that you did and weight? So
I mean, the Kings,
great question. Yeah.
The Kings are pretty big. Those were 2 kilograms, 3 days of printing. We're really bumping up against that oven size thing. I mean, these are pretty big as far as size wise. In general, that 100 is where we need to stay at. Bigger the part, the bigger the problem. So we want to have smaller ones, but you know, like this simple part, you're like, okay, when we have support materials, so like these are made combined. I'm thinking about that multi-material one more and more. That's a good idea. Yeah, 100 would be our starting spot. Now, for those of you that want to have a part that's bigger, that's when you contact us directly. We can make some custom solutions. We can get there. There'll be more iteration though.
Awesome. And I would like to keep it here, maybe throw a couple of last questions, James. Where do you see this type of technology, going as far as, enabling makers like myself that really have printers at home? They're going to use the material, the one spool, 3 kilograms. Is it going to be a change in the amount that is is available in the retail? And if you can touch on that. I know it's a something that you might not be able to share, but if you can share as much as you can, that'll be
of course
great.
So the good news is that 17.4 pH, our new material, does come out on a 1 kilogram spool. Nice. Instead of 3 kilograms, we have 1 kilogram spools. It's gets you a little bit more, the price comes down a little bit more, it gets a little bit more easier to use. Where do I see it going? I see it as another tool in your toolbox. Simple as that. Sometimes you need a drill, sometimes you need a mill, sometimes you need a laser cutter. I see a world for binary metals, like that question talked about, gradiated material structures, hollow parts. You see, everyone talks about additive and no one designs for additive. And I see a need for people like ourselves to come up with the rules for these things. When I look at, when I look at these two, my little bowling pins, this one is 50% the weight of this one. All right, because it's hollow, because it has that, I think this one's gyroid actually, but we don't have the designs for it. We don't have the models for it. I'll get questions about fatigue and things like that. And it's like, how much it takes to get a Moore's sample? These things will have to be tested. Exactly. They'll have to be learned. So I look at it as maybe, it's crazy. The research and development guy wants to do more research and development, but I see a landscape where I myself in my apartment can be doing things that I could not do in a lab. I see a student that didn't have access to the equipment like I was lucky to have, them being able to do it. I see people making their own sculptures, their own art, and not really know how to do manufacturing, and not to hold it like our calculus teachers holding it as a none shall pass until you can take the derivative of both sides. No, I've shown 8-year-old kids how to do this, and they picked it up. I want it to be like that Nintendo. You just pick it up and you know what to do with it. So that's my goal.
Awesome. Wow. Thank you. Thank you so much, James. I wanted to keep a few minutes, shorter. So I don't see any other questions coming in. I'm sure people, go through the information, and yeah, there was a lot. And this is a whole new field. So it's very exciting for myself. Being in the actually professionally working with metals as well as at home now, having access to this material. So it's very exciting. Again, from everyone within our chapter, the audience as well as other chapters, I would like to really thank you for your time. Really appreciate it. It was a great presentation and great coverage, and we'll look forward to hosting events like this in the future.
Awesome. Yeah, like I said before, share my contact detail.
Sure.
You're going to have a bunch. I mean, hopefully you have a bunch. This is only skimming the surface. People, if you have questions out there, I literally do this for a hobby and for money.
All right. Awesome. Jacob is here. Jacob, I'll hand it off to you.
Hey, just wanted to echo Farhad's thoughts, James. Man, for being an overview, I was blown away by a comprehensive, and insightful you'd gotten, and especially for someone who dabbles and frequents in the subtractive side. Really love to hear about that portion of your journey and how you related these metal components, to CNC, and really, highlighted how difficult it would be and how costly. In some cases, given the complexity as compared to going AM, man. And
people don't know. People don't know. Like I said, You know what that cost in CNC? Are you kidding me?
Exactly.
I'll tell you, it cost me $20. I just printed it.
Amazing, man. Hey,
Yeah.
again, just heartfelt thanks. And again, I saw Dual
Awesome.
say, Ryan, everyone who helped promote this event, thanks to everyone. Look forward to the next one.
Absolutely. All right.
Awesome.
James, thank you. Thank you so much. Have a great rest of the night over there.
It's 7
and
o'clock. I'm
everyone
have a beer.
else. Hopefully
Thanks,
you enjoyed
everybody.
that one. Yeah, it was great presentation. Thank you again. And thank you, everyone. Have a great day.
Thanks. Show me. I want to see parts when you're done.
Yeah.
All right.
I'll
Bye,
share.
everybody.
All right. Thanks. Bye. Bye.